Voltaic cells. In a spontaneous redox reaction, electrons are transferred from one species to another, and energy is released in the process. In the example shown, copper metal is produced when zinc metal is added to a solution of copper ions. The zinc metal transfers 2 electrons to a copper ion, and a copper metal atom and zinc ion are produced. Because the reaction is spontaneous, we can get the reaction to do work if we can force the transfer of electrons to occur through an external circuit and device. The key is that these reactions are spontaneous. We call such a setup a voltaic or galvanic cell. A voltaic cell is a cell in which a spontaneous redox reaction transfers its electrons through a wire so that work can be done. A voltaic cell is also called a galvanic cell. Here is a picture of a voltaic cell made out of the reaction we looked at earlier. We will use it to highlight the important parts of any voltaic cell. The first important piece is the external wire connector, which is used to connect one half of the cell to the other half. This is what the electrons flow through. In the diagram, there is a switch to cut off the flow of electrons if desired, and a voltmeter to measure the voltage of the cell. More about that later. The zinc half cell. In a typical half cell, both the oxidized form and the reduced form are present. In this case, the oxidized form is the zinc 2+ ions in the solution, and the reduced form is the zinc metal, which is used as the electrode for the half cell. The copper half cell. The reduced form is the copper metal, which forms the electrode for the half cell. The oxidized form is Cu2+ ions in solution. The salt bridge, which is usually a tube containing a solution of a salt. This may be the most critical part of the whole device. The two half reactions must often occur in separate areas of the cell called half cells. Oxidation occurs in one half cell and reduction in the other. The voltaic cell almost always must separate these two parts so that the transfer of electrons does not occur directly. Oxidation occurs at the anode. Note that the vowels O and A are together. In this case, the zinc metal is being oxidized to zinc ions, as shown in the highlighted reaction. Reduction occurs at the cathode. The consonants R and C are together. In this case, the copper ions are being reduced to copper metal in the reaction highlighted. Once electrons start to flow, a problem quickly develops. The buildup of positive charge in the zinc half cell and negative charge in the copper half cell stops the flow of electrons. The salt bridge contains a salt solution, and the ions move towards one half cell or the other to balance the charge and keep the electrons flowing. The salt is chosen so that the ions of the salt will not react in either half cell. The cations move toward the cathode because that half cell is negatively charged. Anions move toward the anode because that half cell is positively charged. Both types of ions move in opposite directions to balance the charge in each half cell. Since oxidation occurs at the anode loses electrons. These electrons flow through the wire toward the cathode. The zinc metal atom that loses the electrons becomes a zinc 2+ ion and moves into the solution. The electrons flow through the wire and enter the cathode, making it negatively charged. A Cu2+ ion picks up the electrons from the cathode, gaining electrons and therefore becoming reduced, and becomes a neutral atom of copper metal on the cathode. There is a useful analogy that can be drawn between the electron flow through a wire and water going over a waterfall. In a waterfall, the water falls a certain distance. The fundamental difference between the water at the top of the waterfall and the water at the bottom is the change in gravitational potential energy. The water will only flow one way in the waterfall, from higher potential energy to lower potential energy. In a similar way, the electrons move from a region of higher electrical potential energy to a region of lower potential energy. Only this direction is spontaneous. Another part of the analogy is that the change in gravitational potential energy for a mole of water going over the falls does not depend on how much water goes over the falls, but only on the height of the falls. In the same way, the change in electrical potential energy for a mole of electrons going through the wire does not depend on how many electrons flow through the wire, but only on something called electromotive force, or EMF for short, for the cell. EMF is the difference in electrical potential energy between the anode and the cathode per unit charge. It is also called cell potential and has the symbol capital E sub cell, or just capital E. This can be confusing since capital E is also used for internal energy, but the context of the use is usually pretty clear. The units of cell potential are volts. 1 volt equals 1 joule per coulomb. Tables of the standard reduction potentials for various reactions can be found in various places. The standard reduction potential is the voltage of the reduction half reaction. We cannot actually measure the potential, or voltage, of a half reaction by itself, since reduction never occurs without oxidation. There must be a transfer of electrons. So, we measure a particular half reaction against a standard, the standard hydrogen electrode. The standard hydrogen electrode is the reaction between hydrogen ions at 1 molar concentration and hydrogen gas at 1 atmosphere pressure. The voltage of the standard hydrogen half cell is, by definition, 0.00 volts. Hydrogen is chosen as a standard because, first of all, its potential is about halfway between the potential of the half reaction that is most easily reduced and the potential of the half reaction that is most difficult to reduce. And second, it is fairly easy to set up and run. A more complete table is found in your book in Appendix E. Because cell potential is based on the potential energy per unit of charge, it is an intensive property. This leads to 2 important consequences. 1. The voltage does not change when we multiply the equation. So the voltage for the silver half reaction is the same whether 1 or 2 silver ions are reduced. 2. When we reverse the half reaction, the sign of the voltage changes. The voltage for the reduction half reaction for silver ion to silver metal is plus 0.799 volts, while the voltage for the oxidation half reaction for silver metal becoming silver ion is minus 0.799 volts. This leads us to 2 ways of thinking about finding the cell voltage. We can either subtract the reduction potential at the anode from the reduction potential at the cathode, meaning that we would need to identify which electrode was which, or we can reverse the half reaction that is being oxidized, changing the sign of the half cell voltage, and add the 2 potentials. Both methods are illustrated in this example of a zinc-copper cell, which is called a Daniell cell. The zinc is oxidized at the anode, and the reduction potential for the zinc is minus 0.76 volts. Since we need to reverse the reduction half reaction, the voltage for the oxidation half reaction is plus 0.76 volts. Copper is reduced at the cathode and has a half cell reduction potential of plus 0.34 volts. By the first method, we subtract the reduction potential at the anode, minus 0.76 volts, from the reduction potential at the cathode, plus 0.34 volts, giving us plus 0.34 minus negative 0.76, or plus 1.10 volts. By the second method, we add the reduction potential to the oxidation potential, giving plus 0.34 volts plus 0.76 volts, which equals plus 1.10 volts, the same result as before. I personally prefer the second method because A, you are working with the actual voltages of the half reactions that are actually occurring in the cell, and B, you don't need to identify which reaction is the oxidation and which is the reduction to use it. Just identify what the two half reactions actually are, and if the half reaction is the reverse of the reaction given in the table, change its sign. If we remember that the oxidizing agent is the substance that contains the atom that gets reduced, then the oxidizing agent is in the reactants in the table of reduction potentials. The strongest oxidizing agents have the highest, that is the most positive, reduction potentials. On the other hand, the reducing agent is the substance that contains the atom that gets oxidized. So the reducing agents are in the products in the table of reduction potentials. The strongest reducing agents have the lowest, that is the most negative, reduction potentials. The greater the difference between the half cell voltages of the two half reactions, the greater the voltage of the cell.